the frictionless ramp example. And so with this, we're going to start by saying we've got a box whose mass is 2.5 kilograms sliding down a frictionless incline angled at 9.5 degrees above or with the horizontal. It slides down the ramp that is 3 meters long. So first things first, we're asked to draw a free body diagram for the box. So first force acting on the box is going to be the force of gravity, which is going straight down with a force of mg. And then we know that there's a normal force going along the line that is perpendicular to the ramp, and that force normal is going to go right in here. And if we want to be paying attention, you can remember that this angle in here is your angle of inclination, meaning that angle is 9.5 degrees. Okay. Now, on the diagram in part A, using a different color, it's me, of course, it's a different color. So let me go with nice bright red. Okay, there we go. There we are. And I want to draw in a vector that indicates the displacement vector, which would be down the ramp. Okay. Now, when we're going to figure out the angle in between the weight and the displacement, which is part C, we're going to need to look at this angle here. And keep in mind that the displacement is along the ramp, and this line here is perpendicular to the ramp. So this whole area is going to be a 90-degree angle. So this 90-degree angle is going to be equal to the theta in between the displacement and the force of gravity, and add to that the 9.5 degrees that is the angle of inclination, meaning that theta is going to be 90 minus 9.5, making it 80.5 degrees, or theta is 80.5 degrees. Then we go to figuring out what's the angle between the normal force and the displacement. Well, that's kind of on the obvious side, because the normal force, by definition, is perpendicular to the ramp, and the displacement is along the ramp. So theta for the normal force is going to, so theta for gravity, 80.5, theta for the normal force is going to be 90 degrees. So how much work is done by the normal force? Well, that's going to be 0 because they're perpendicular to each other. Woohoo! Then we can look at what is the work that's being done by the weight. Well, work done by gravity, which would be the work done by the weight, would be the force of gravity, which is mg, times the displacement d, times the cosine of the angle in between them. So, looking back at our graph, at the statement of the problem, the box on the ramp is 2.5 kilograms, g is 9.8 meters per second squared, and it's displaced by 3 meters sliding down the ramp. And I think you can remember from above, and if not, just go back and look. The angle is 80.5 degrees. A little punchy on our calculator gives us a work equal to 12.130999903, or that the work done by gravity is 12.1 joules. Okay, so what is the net work done on the box? Well, that's going to just be the work done by the normal force, which of course we know to be 0, plus the work done by gravity. In other words, it's going to be 12.1 joules. And then finally, if the box is released from rest, what is the final velocity of the box? Now, you could go back and figure out the net force to determine the acceleration and then use the kinematics equation v final squared is equal to v initial squared plus 2a times x final minus x initial. But nobody wants to do that, okay? We want to do this quick and simple, okay? So this is where the work kinetic energy equation is your best friend, that the net work is equal to the change in kinetic energy, meaning the work net we just found is going to equal 1/2 mv final squared minus 1/2 mv initial squared. But we just said that it started from rest, so the initial kinetic energy is 0, which means the final velocity will be the square root of 2 times the work net divided by the mass. Now keep in mind this is only going to be true if it's starting from rest. Not everything starts at rest. Some things are moving before work is done to them in these problems. So that's going to give us a velocity is equal to the square root of 2 times. Now, remember, you want to use the full number so that we have as few of rounding errors as possible. And our mass for the box was 2.5, giving us a velocity of 3.11525, on and on and on, or that the final velocity is 3.12 meters per second.